computing the determinant can be kind of tedious. So now we're going to look at some techniques to make the determinant a little less painful. So for starters, we saw in the previous section that if you take the determinant of a triangular matrix, whether it was upper triangular or lower triangular, this is the product of the diagonals. So we can use that fact along with elementary row operations. So we want to know what the elementary row operations, what effect those have on the determinant of a matrix. So if let's say we have a matrix A, and we use an elementary row operation to turn it into a related matrix. Let's call the related matrix B. I want to know how those two are related. Well, if you switch two rows, then the determinant of A is the negative of the determinant of B. You can go through a few examples to convince yourself of this. If we scale a row, so if we took A and we multiplied a row by a scalar C, then the determinant of A is C times the determinant of B. So it scales well with scalar multiplication. And if we take a matrix A and we add a multiple of one row to another, if we add a multiple of one row to another, this actually doesn't change the determinant at all. That's kind of nice. The determinant of A is the same as the determinant of B. So we can use this to take some of the headache out of determinants. For example, let's say we've got, let's make this kind of big, 1, 2, 3, 5, 4, 6, 7, 8, 9. If we wanted to take the determinant of this matrix, what we could do is we could use our row operations. We could maybe multiply the first row by -5 and add it to the second row. So that'll leave the first row unchanged, 1, 2, 3. -5 plus 5 is 0. -10 plus 4 is -6. -15 plus 6 is -9. And now the same way we can change the bottom row. We can multiply the first row by -7 and add it to the bottom. So -7 plus 7 is 0. -14 plus 8 is -6. -21 plus 9 is -12. Okay, so that makes things a little bit nicer. And by the same token, we can also, say, multiply the second row by -1 and add it to the bottom row. So that says this is the same as 1, 2, 3, 0, -6, -9. Now if we add 6 to -6, we get 0. If we add 9 to -12, we get -3. Okay, so this matrix right here is triangular. That's good. And the determinant of this matrix is just the product of the diagonals, which is 18. So if we look at the previous step, how we got here is we added a multiple of the second row to the third row. So that's using the elementary row operation number 3, which doesn't change the determinant. So I know the determinant is still 18. Okay, also, for the first rule, we added a multiple of the first row to the second row. That doesn't change the determinant. And we added a multiple of the first row to the third row. That doesn't change the determinant either. So the determinant of this matrix is 18, which we got without actually having to expand out all of the various minors and cofactors. So this can be a trick to help you save a lot of time, using those elementary row operations to turn your matrix into a triangular. And we also have some quick ways to determine that the determinant is 0. So first off, if A has a row of zeros, so for example, if we have the matrix 1, 2, 3, 0, 0, 0, 4, 5, 6, then the determinant is 0. Okay, if one row is a multiple of another, Well, if one row is a multiple of another, you can use elementary row operations to completely get rid of one of your rows and turn it into a row of zeros. So we know it's going to be, the determinant of that matrix will be 0. And also, it turns out one of the properties of determinants is that the determinant of A is the same thing as its transpose. Now what that means is that you can apply these same properties to columns of a matrix. So if A has a column of zeros, its determinant is 0. And if one column is a multiple of another column, the determinant is also 0. So these are some quick ways to help save some of the headache from determinants.